Hello everyone, we are the Vicor Corporation team, and today we will be presenting to you our project, the Standalone Cable Checker. The Standalone Cable Checker project was overseen by our technical directors over at Vicor Corporation. They were Daniel Hartnett, who's from ELE's class of 2021, Alfred Binder, and Nathan Shake, who was from ELE's class of 2020. The team consists of 3 members: myself, Alan Lee, an electrical engineering major, Ricky Lau, computer engineering major, and Griffin Malikan, electrical engineering major as well. Vicor Corporation is a company based in Andover, Mass, with facilities stretching all across the world. Here, they manufacture, deliver, and design modular power components to the market and various industries. If you aren't already familiar with Vicor Corporation, they are a vendor for industries such as automation, industrial, high-performance computing, defense, vehicles and transportation, aerospace, and network infrastructure. As a supplier for the previously mentioned industries, Vicor Corporation produces and manufactures a large amount of ICs that all have varying capabilities. This also requires for numerous cable types for interfacing with these PCBs. This may cause for the debugging process for each system to be tedious and time-consuming, as not only do they have to test the PCBs, but also the cables that interface with them as well. Throughout these semesters, we have been tasked with creating a standalone cable checker that will allow for multiple cable connections for a wide variety of cables. This would hopefully alleviate some of the burdens and pressures placed upon the test engineers over at Vicor Corporation, which would ultimately cut down on lead times. Some of the key features of our project include multiple cable interfacing for the wide variety of cables that Vicor Corporation uses, a UI to display relevant information, and various testing modes to test the functionality of a cable. Ultimately, our ABO, or anticipated best outcome, was achieved. Below are 2 pictures of our PCBs that have been finalized, tested, and demonstrated to our technical directors over at Vicor Corporation for functionality. On the left side, you can see that there is a 156 pin out cable checker. On the right side is a cable checker for the various rainbow cables that Vicor Corporation employs in their products. In order to ensure that the Vicor Corporation team met its ABO, or anticipated best outcome, by the end of the semester, we have set many milestones for ourselves, which are also our key technical accomplishments. This includes benchmarking our components, such as our ICs or microcontroller, prototype development on a protoboard in order to ensure that our proof of concept functioned, custom footprints for the footprints and schematics that did not already exist in the Altium library, PCB design, which included PCB prototype fabrication, testing, and redesign, as well as the final fabrication of the PCBs, and also development of the final program for the SCC, or Standalone Cable Checker. There are many significant economic implications upon the completion of our project, the Standalone Cable Checker for Vicor Corporation. This includes reduced testing lead times for Vicor Corporation, as test engineers over at Vicor now have a plug-and-test solution for many of the cables that they use on a day-to-day basis. This also means that there is improved resource allocation, as the test engineers no longer have to probe each individual pin for their cables. Instead, they can just plug and test, meaning they can work on other projects in the meantime. This also implies that there are faster turnaround times, as the test engineers over at Vicor Corporation can now narrow down what is wrong with their system. Down below, you can find the block diagrams dictating the logic for our project, the Standalone Cable Checker. On the left-hand side, you can see a simplified version dictating our logic of our project and program. First, the user selects the pin count for the cable. The Arduino then reads this user input, then sends signals throughout its pins, which are then split up by demuxes that travel through a cable. These signals are then recombined by a mux on the other side of the cable, which the Arduino then reads and verifies if it's good or bad. Information pertaining to the signal veracity is displayed throughout the LCD. On the right-hand side, you can see a bit of how the logic is regarding the splitting of signals through our demuxes and muxes. To ensure that our ABO, or anticipated best outcome, was met, the individual team members of the Vicor Corporation team all developed towards the technical development of our project, the Standalone Cable Checker. Initially, two prototype designs were created. The first design was more of a proof of concept, which utilized a simple AND gate design. This design combined the signals coming from the AND gate and lit up one of 6 LEDs using a manual incrementation style. Later on, after finishing the design, we developed a multi-level demux and mux design that is much closer and resembles more of what we have in the final project. This design used a greater degree of signal manipulation through address lines, allowed for automatic and manual incrementation, displayed information through the LCD, and also used a 2-level design for the muxes and demuxes by concatenating them. Upon completion of the prototype design on the breadboards, I then went on to design the PCB schematics. There are 3 main sections dictated here in the pictures shown below for the schematic design. First is the main schematic page, which has all the high-level components and entities for this project. This includes the Arduino, the LCD, the switches, the buttons, and the first level muxes and demuxes. Then, I went on to design custom footprints that were not already in the Altium library. Mainly, this was what the 156 pin-out cable connector header that did not already exist. Afterwards, I would then create the schematics for the demuxes and muxes. Although only the demuxes are shown here, the muxes are functionally similar, with the only difference being that the outputs are switched to inputs instead. Additionally, there are 3 pages of demuxes. This is also the same for the muxes. On completing the PCB schematic for the 156 pin out cable checker, the next step was to create and finish the layout. Down below are the finalized versions of the PCB layout. On the left hand side is the 2D model with the routes, and on the right hand side is a 3D model. Of course, these only show the finalized versions of the PCB and do not show the many iterations that have been underwent throughout the design process. This finalized version is drastically different from the one shown at the end of the previous semester during the Capstone Symposium. After completing the layouts, the next step was to fabricate the board and assemble it. Down below, you can see that the blank PCB has been fabricated, and on the right hand side, you can see that the ICs have been implemented into the PCB. Upon finishing implementing and soldering on all the components for the 156 pin out standalone cable checker, the next step was to verify its functionality. As you can see below, the cable is plugged in and the program is running, and it displays that the cable is good. I will now hand off this presentation to my partner, Griffin Melican, who will be presenting his own individual contributions to the technical development of our project, the Standalone Cable Checker.
Thank you, Alan. So when we left off back in December at the symposium, I had just started designing the prototype PCB board for the multiplexer logic you see here on the right. It was frankly a complete mess, and it was going to take some time to make the rat's nest into something workable. Here you can see the final prototype design. On the left you can see the 2D design layout, and on the right is the 3D model. The board consisted of 6 total layers: top and bottom signal layers, ground plane, power plane, and 2 additional signal layers, similar to Alan's layout. It was capable of interfacing with 3 different cable types, and could run both continuity and short tests. Data was displayed on the LCD in the bottom right corner. An indicator LED was used for signal verification. And here is the final constructed prototype board, and a demonstration of it running a continuity test on a 50-pin FRC cable. As you can see, it passed. You may also notice a critical design error with the Arduino unit, as it is conflicting with a few muxes underneath its power port. This was one of many noted design changes that would be implemented in the next revision. Now we've arrived at the improved and final revision for the SCC for the 26, 34, and 50 pin cables. Again, on the left is the 2D design layout, and on the right is the 3D model. A lot has changed. To start with, the board went from 6 layers to 4 layers, consisting of just the top and bottom signal layers, a ground plane, and a power plane. This required a new and more orderly method of routing, which I can give thanks to Vicor technicians for showing me how to do so. All muxes were moved in between the headers, and we were able to remove 2 of them to simplify the logic. The Arduino is rotated 180 degrees into its proper orientation, and we included new features such as a 4-way switch for mode selection and a much needed start button with LEDs. More importantly, the correct headers were adapted for the 34 and 50 pin cables, which can be seen on the bottom right in the 3D model. Lastly, we have the final constructed SCC platform. Aesthetically, it looks much cleaner than its predecessor, and after a bit of hardware and software troubleshooting, it works like a charm. In this demo, the 34 pin cable successfully passed the continuity test. Now I will hand the presentation over to our other partner, Ricky Lau, who will go into the software aspect of the project.
Thank you, Griffin. With the PCBs for the 2 testing circuits completed, it all comes down to implementing the firmware for these 2 boards. The progress of the firmware from last semester was already close to completion, but it had to be ported to ensure functionality for both boards. This new heavily simplified flowchart of the SCC is the result of those changes. This slide shows the class implementation for the larger board and the smaller board, as well as example outputs. These are similar to last semester's class, except for the addition of a cable size method and an additional mode. The previous increment mode was dropped as it was decided it was not necessary, with the main functionality already existing for the auto mode. Replacing it is a short testing mode, where the user can test a short of a pin with any other pin. The output on the top right shows what the mode is capable of. Here, pin 5 was shorted with pin 3, and pin 8 was shorted with pins 1 and 2. Of course, these 2 boards are capable of this mode, as well as the original continuity checker for the given cable size selected. This can be seen on the outputs on the bottom right. Here, this is a more in-depth look at the implementation. All that should be taken away from this slide is that the ports of the firmware are nearly identical, aside from the additional mux/demux layer in the 156 board. The same hierarchy of control of determining cable size, then determining the mode, then executing over the cable is all the same. Again, with the only real difference being the cable size. Quickly, looking back at the flowchart from last semester is a testament to how we maintained the control hierarchy until now. Rather, instead of the ability to increment a pin counter, those pathways are simplified to look more similar to the continuity checker path. To reiterate, as of now, we could safely say that the anticipated best outcome was achieved. After extensive testing of the 2 boards, we have verified the working operation of all required cable sizes for both modes. Thus, Vicor Corporation can easily benefit from our cost-effective solution to test their cables before putting them to use in their automatic testing equipment. Finally, we'd like to thank those that helped us along the way. Technical Directors Alfred Binder, Nathan Shake, and Daniel Hartnett, as well as a special thanks to ELECOMP Capstone Director, Dr. Harish Sunak. Thank you.